There's this invisible force at work all around us, all the time. It shapes everything from the coffee in your mug to the most complex experiments in a chemistry lab. It's called solubility, and honestly, it's one of those fundamental concepts that just quietly runs our world. So let's dive in and see how it works. Have you ever actually stopped to wonder about this? I mean, you stir sugar into a hot cup of tea, and poof, it's just gone. But then you try the exact same thing with a cold glass of iced tea, and you end up with that sandy sludge at the bottom. It's such a common experience, right? And it's the central mystery we're going to solve today. The answer to our whole tea problem comes down to this one word: solubility. It's just the scientific term for the ability of one thing, the solute, to totally dissolve into another, the solvent, and create a perfectly uniform mixture. This really simple idea is the absolute key to understanding our tea mystery, and as you'll see, so much more. Okay, so what is actually happening when something dissolves? I mean, what's going on that we can't see? To get it, we need to zoom in. No, like way in, down to the molecular level. We're about to see the tiny microscopic action behind this everyday magic. So let's break down the key players here. It's super simple. In our tea example, the sugar, that's the solvent. It's the stuff that gets dissolved. The water is the solvent. It's the one doing all the dissolving work. And that perfect sweet tea you end up with, that's our solution. Easy, right? Now, the real hero of this whole story is the water molecule itself. See, water is what we call a polar solvent. All that means is it has a slightly negative end and a slightly positive end, kind of like a tiny magnet. This little imbalance of charge, that's its superpower. It's the secret to its incredible dissolving power. So picture this: you drop a salt crystal into water. Immediately, these tiny polar water molecules just swarm it. Their positive ends are attracted to the negative parts of the salt, and their negative ends grab onto the positive parts. They literally surround these little pieces and just pull them away from the crystal, dismantling it piece by piece. Honestly, the best way to think about it is like a molecular dance. The water molecules are the confident leaders on the dance floor. They just waltz right in, take the little salt ions by the hand, and lead them away from the group until the whole crystal structure is broken up and everyone is dancing all throughout the water. But just like our iced tea proved, this dance definitely has its limits. You can't just keep dissolving stuff forever and ever. So what happens when that molecular dance floor gets a little too crowded? A solution basically has two main states. When you first start adding sugar to your tea and it disappears right away, you've got an unsaturated solution. There's still plenty of room on the dance floor, but once you hit that point where no more sugar will dissolve, no matter how much you stir, that's it. You've created a saturated solution. The solvent is totally full. But wait, there's a third, kind of magical state called a supersaturated solution. This is where it gets cool. You can trick a liquid into holding way more solute than it's supposed to. You usually do this by dissolving a ton of stuff in a hot liquid and then letting it cool down really, really carefully. It's totally unstable. Think of making rock candy or those reusable hand warmers. The second you disturb it, bam, all that extra stuff suddenly crystallizes right out of the solution. So how do chemists keep track of all these limits? Well, they use a tool called a solubility curve. It's basically a graph that shows you the exact saturation point for something at any given temperature. That line you see, that's the limit. If your solution falls below the line, it's unsaturated. If you manage to get it above the line without it crystallizing, you've pulled off that tricky supersaturated state. And here we are, right back at our original question about the tea. For most solids, like sugar, as the temperature goes up, solubility goes up too. The hot water molecules in your tea are buzzing with energy, they're moving faster, they're colliding harder, and they're way more effective at pulling those sugar molecules into the solution. The slow, sluggish molecules in your cold iced tea, they just can't keep up. Mystery solved. Okay, so we've cracked the tea mystery, which is great, but why does any of this matter beyond our kitchen? Well, as it turns out, this simple concept is critical to, well, pretty much everything. Let's take a look. I mean, seriously, think about it. Cooking, it's all about dissolving flavors to make food taste good. Medicine, a pill does nothing if its active ingredients can't dissolve into your bloodstream. Cleaning your clothes, detergents work by dissolving in water to lift away grime and dirt. And for environmental scientists, understanding how pollutants dissolve and move through rivers and oceans is absolutely crucial. It is everywhere. And this isn't just some abstract idea. It is big business. The entire food processing industry pretty much runs on mastering solubility. You know, the perfect smooth texture of a sauce, or the fact that your sports drink is clear and not a gritty mess. That is all thanks to chemists who have precisely engineered the solubility of every single ingredient. So for our last section, let's look at how chemists take this concept and turn it into an amazing practical tool. You can think of it like a playbook for predicting chemical reactions before they even happen. Chemists have this incredible set of guidelines known as solubility rules. You can just think of them as a cheat sheet. They help predict what's going to happen when you mix two different liquids together. Specifically, these rules tell them if mixing two clear solutions is going to suddenly form a solid that just drops right to the bottom. And that solid, by the way, has a name, a precipitate. And here's a super simplified version of that cheat sheet. The main idea is that some ingredients, like anything with sodium or nitrate, almost always make compounds that dissolve super easily. Others, like carbonates, usually form solids that won't dissolve at all. By knowing these basic patterns, a chemist can be really smart about how they mix things, either to keep everything dissolved or to purposefully create a solid that they want to separate out. So the next time you stir your coffee, or take a vitamin, or even do a load of laundry, you'll know about the invisible dance happening right in front of you. Which, leaves us with one last thought. If this whole molecular dance is such a powerful, unseen force, what other invisible principles are out there shaping our world every single day, just waiting for us to notice?